Hey folks, in lesson 20, we're going to start looking at systems that have multiple particles. So far, chapters 1 through 5, we've gone with only a single particle, and now we're going to start considering what happens when we have multiple particles that we need to keep track of, that we need to take care of, and that interact within a system. And we'll start simply by applying Newton's second law. So let's go with a single particle to begin with. And I'm going to change the notation a little bit, and we're going to call this particle I instead of particle P like we've done before, and you'll see why in just a moment. But if we've got particle I, then we can certainly apply Newton's second law to this the same way that we have over and over before, because we're always saying that the sum of the forces on particle I is going to be equal to the mass I multiplied times the acceleration of I with respect to O as observed in the inertial reference frame. And we would use all the standard convention in which we'd find a position vector of, so it's r of I with respect to O, and then our velocity of I with respect to O as observed in the inertial reference frame, and our acceleration of I with respect to O as observed in the inertial reference frame. So nothing so far is new. But let's put another particle on our plane. Let's call it J. And so we can continue doing this where we have all the forces on particle J are equal to the mass J, acceleration of J with respect to O as observed in the inertial reference frame, and find all of our position vector, velocity vector, and acceleration vectors the same way. One of the first things you should notice here is that keeping track of our subscripts is really important. Now, as we've done example problems in these first 5 chapters with a single particle, oftentimes I've just dropped the subscript from our m's, and we've just said, well, here's our mass, it's the only mass that we're dealing with. But it's important from now on to be very specific about which mass you're talking about and which forces are appearing on what particle. So we're really starting to use this notation. Now let's apply forces to these particles. So on particle I, mass I, we can have a force that we're going to call F sub I, and this is going to be an external force. Now, I'm going to juxtapose that with an internal force. So when I say external force here, it's external from the system of particles. We also have the potential to have forces that are acting between the particles. So that means we also would have a force here that would be Fi, J. And so Fi, J, if we state that clearly, is the force on particle I applied by particle J. And so that's an internal force, and that means that we have to have an equal and opposite internal force that would be the force onto J applied by I. And that simply obeys Newton's third law, in which every action or every force has an equal and opposite force. Every action has an equal and opposite reaction. And so we can also put an external force on J. So Fj external. And if we put these down in our Newton's second law, our formulation of Newton's second law, then we don't have Fi any longer, but we've separated that now into F sub I external forces plus the internal forces applied by all the other particles, which are Fi, J, and then on Fj we have an Fj, which are external forces, and then that's plus the internal forces Fj, I. And so we can continue to do this perpetually, really, in which we get a particle K, and on that particle K there are external forces, Fk, and then we also have the internal forces that we need to account for. And so these would be the forces onto K by particle I, and then we have the forces onto I by particle K. We have our internal forces between K and J, so the forces onto K by particle J, and then the force onto J by particle K. And we need to come down and add these to our equations as well. So this would be plus Fi comma K, and then plus Fj comma K. And then we need another equation of motion, or another application of Newton's second law. And so you can see that this gets a little bit out of hand if we keep writing F equals ma over and over and over and over. So instead, to account for this, we're going to add some notation here in which we're saying that the mass of particle J, and this is any particle J, not just the particle that we have here, of particle J multiplied times the acceleration of J with respect to O, as observed in the inertial reference frame, is going to be equal to the sum of the external forces on that particle plus all the other internal forces by all the other particles that are there. And so the notation that we have is a discrete sum where we're adding up the force J comma I, and then we're varying I across all the other numbers. And so this is where N is equal to the number of particles. Okay? And so you can take a look and see that that's exactly what we're doing here in what's now the upper right hand part of the screen. And then there's also one other condition, and that's where F of J comma J is equal to 0. And that's essentially just saying that the particle itself can't exert a force on itself. Now this is simply a fancy way of applying Newton's second law to every particle that we have within a particular system. And so we can add up as many particles as we want, and we'll be able to use this formula for every single application of Newton's second law. Now don't let the notation of F, J, comma I fool you. Okay? So these are simply forces by constraints, like in wires or strings. They're normal forces, or they could be springs between the masses. And there's an example in the book that talks about the two-body or the in-body problem. And so those forces between those particles are going to be gravity. And so we're simply going to model this, or model these internal forces the same way that we've done before, the same way that we even did in statics, where we would cut structures and then we would have an equal and opposite force. Alright, let's set up an example. So here we've got example 6.2, which is entitled The Crane from the book. And so what this is asking for is simply to derive the equations of motion for the model of that's shown below. And so the reason why there are equations of motion plural, is because we have two masses. There's a mass Q and then there's a mass P, but then there are also 2 degrees of freedom, in which Q is defined by the linear position, or the Cartesian coordinate x, and then P is going to be defined by the angle of P, or the angle of this pendulum, is going to be defined by the angle theta. And so to do this, we're simply going to solve F equals ma twice. And so we have that F of Q is equal to the mass of Q, be sure you put the subscripts, acceleration of Q with respect to O, as observed in the inertial reference frame, and then we're also going to solve the forces on P are equal to the mass of P multiplied times the acceleration of P with respect to O, as observed in the inertial reference frame. And because this is a system of particles, the sum forces on Q are going to be a combination of external forces and internal forces, and the sum forces on P are going to be a combination of external forces and internal forces as well. And we identify these by drawing our free body diagrams. So our free body diagram of Q, and be clear which free body diagram you're drawing, is going to look like this, whereas our free body diagram of point P is simply going to be a circular mass. And so on the free body diagram on Q, we need to have our mass, our force due to gravity, and that's mq multiplied times g. Our inertial reference frame has EY pointing up, so that's going to be in the negative EY direction. And then we need to have a normal force, which is in the positive EY direction. And then there's going to be a force due to the tension in the string, or in the pendulum itself. And so that force, we'll point it along the ER direction. We'll call that T in the ER direction. And so likewise, when we're drawing our free body diagram of P, it's going to have the mass P multiplied times gravity in the negative EY direction. And then the only other force applied to it is going to be the equal and opposite force, tension, in the ER, in the negative ER direction. And so we see here that our external forces are gravity, so these are our external forces, and then this would be our internal forces, anything that shows up twice in your free body diagram, or your free body diagrams, plural. And so you'll set up this problem just how we have in the past, in which we have R of Q with respect to O is going to be equal to X in the EX direction, and then R of P with respect to O is going to be equal to X in the EX direction plus L in the ER direction. You're going to solve for your kinematics, solve for F equals ma, and then we're going to get these two equations of motion when all is said and done. So x double dot is equal to this expression in which the mass of P multiplied times g sine theta cosine theta plus mass of P L theta dot squared sine theta divided by the quantity the mass of P sine squared theta plus the mass of Q. This is a big expression for x double dot, but you should see things in here that you recognize. You know, when you see this L theta dot squared, you should recognize that that looks a lot like a centripetal acceleration, and then we've got our force due to gravity on P, and then we're being scaled by these mass terms. And so you can see that, you know, what's happening here is we're kind of projecting each of these accelerations around onto this linear acceleration x double dot. And then also notice that x double dot isn't a function of x. It's only a function of the pendulum state, which is theta dot and theta. And so what this is saying is that whenever you change the angle of the pendulum, even if you just pull it back, you don't even have to have any angular velocity with that, it's going to accelerate that mass P, or that mass Q, I believe. And so you can see that in the system is that even if you just pull the pendulum back, then what should happen is that this pendulum is going to accelerate. Okay, so if you pull it back and let it go, then the mass Q is going to accelerate back and forth. It's going to have somewhat of an oscillatory motion, okay, and that's only by moving the pendulum. Let's write out our equation of motion for theta double dot. And here again you should see things that you recognize. So in the first part, it's minus g over L sine theta. So minus g over L sine theta, we know, according to the coordinates that we've used, is the equation of motion for a simple pendulum that's not attached to anything, but is attached to an inertially fixed point. And so if this is our simple pendulum, when it's attached to an inertially fixed point, the time in which the pendulum itself is going to behave just like a simple pendulum and have no, funky terms that are happening here is when this is equal to 0. And so when this is equal to 0 is simply when x double dot is equal to 0, and we can see that because this term here is the x double dot term. And so let's just make sure that makes sense. If we take a look at our pendulum again, is that if our mass Q has an acceleration, or if x double dot is equal to 0, that means that Q has no acceleration or it's fixed. So it doesn't have any acceleration. It's either moving at a constant velocity or it's fixed. So if Q is moving at a constant velocity, then this pendulum is free to swing just like a pendulum. But if Q is moving with any acceleration at all, then that's when this second term is coming in. And this is actually not unlike when we were talking about the car that was accelerating and then how your fuzzy dice move back or how it swings. But instead what we've got here is that if the block itself, Q, is at a constant velocity or fixed, it's acting just like a simple pendulum. And another difference between these two equations of motion to notice is that whereas x double dot was fully dependent upon the state of theta, so theta and theta dot, the state of the pendulum, theta double dot isn't at all dependent upon the state of the block itself. So x dot can be anything, and x can be anything, the position or velocity can be whatever, but the only thing it's affected by is actually just the acceleration of x, not the position and not the velocity. So I encourage you, whenever you get an equation of motion, even if it looks complex and looks complicated, find things in the equation that you recognize and try to understand how those fit. And especially when you have two different equations of motion, find out how they fit together and how they're coupled together and how they're not coupled together. And that can give you insight into the system and continue to demystify acceleration. So we didn't work through this example in totality, but you've got enough room in your notes to do that. I encourage you to do that. The way I've written these equations of motion are a little bit different than in the book. And so I think that you'll arrive at these much easier than how they're expressed in the book. One thing you may have noticed so far is that if we apply Newton's second law to every single particle using F equals ma over and over and over and over, and as you work through that last example and derive those equations of motion, is that this just gets tedious and it gets very cumbersome. But one thing that we can do is we can sort of back out and start looking at our entire system of particles at one time. And the first way that we're going to do that is to look at this in the perspective of linear momentum of the entire system. And we call that total linear momentum. And so how we would get there is we're going to take our equation that we have here, which is mass of any particle multiplied times the acceleration of any particle is equal to the external forces and so forth, and we're going to turn this into our momentum equation. And recall that we did that simply by taking the integral of the entire of everything from time 1 to time 2 and integrating that over time. Now, just as a reminder, we're only doing this for a single particle right now. And so what we get out of this is we're going to get our momentum equation for this particle using this notation, where we're going to keep our external forces and our internal forces separate. We didn't do that before, so that this is going to be a little bit new. So that's going to give us our mass of particle J multiplied times our velocity of particle J with respect to O as observed in the inertial reference frame at time 2. Remember, that was on the left-hand side of the equation. So that's equal to the mass of particle J multiplied times the velocity of particle J with respect to O as observed in the inertial reference frame at time 1. And now, instead of having just an impulse or just the integral of the force, we're only going to consider impulses. Remember that impulses were really our most useful form of this. And we're going to have the impulse due to external forces. And so we're going to use the same notation as before, which was an F with a bar on top, J, external. So that's the impulses due to external, the impulses due to external forces, put our time 1, time 2, so across that time, and then plus the sum of all the impulses due to our internal forces. And so this will be F impulse Ji. So it's the impulse on particle J by particle I, and we need to put our time 1, time 2. And so remember, we can use our notation in which we call this P. So this is P of J with respect to O as observed in the inertial reference frame at time 2. And then this guy is P of J with respect to O at time 1 as observed in the inertial reference frame. And so let's take all of these momenta. So if this is the momentum of a single particle J, and we've got n number of particles, then let's add up all the momenta for everything. So we'll just make a big summation of j is equal to 1 to n. And that's going to give us the total linear momentum of the system, because we're taking the individual momenta of each particle and adding them all up. And so our expression for total linear momentum is PO at time 2, okay, as observed in the inertial reference frame. That's our total linear momentum at time 2 is equal to PO at time 1 plus the impulse of all of our external forces. So this is on the entire system now. So when we do this, we're simply dropping the subscript j, because it's not j anymore, but it's all of the external forces on the system. And then when we add up all of the impulses of all of our internal forces, remember that for every fj comma I, there's an equal and opposite fi comma j. So there's an equal and opposite impulse. And so this term ends up being 0 because all of the internal impulses are going to cancel out. And so here's our final expression for our total momentum, total linear momentum. And to repeat that, it's the total linear momentum at time 2 of the system is equal to the linear momentum, total linear momentum at time 1, plus all of the impulses that are given to the system by external forces only. So that means any internal forces, any constraint forces that are internal, any springs, any dashpots, dampers, anything like that, don't contribute to the impulse that would change the momentum of the system. So the other piece that comes out of this is that the total linear momentum of the system is conserved when all of the external impulses are equal to 0. So the total linear momentum at time 2 is equal to the total linear momentum at time 1 when we have no external forces applied, or there's no impulses applied by any external forces. Now, this means that linear momentum is conserved. Now, unlike when we were dealing with a single particle, this doesn't mean that every single particle is going to maintain straight line motion or be stopped. It doesn't mean, when we had a single particle, it meant that a single particle wasn't accelerating, and so we were obeying Newton's first law. In this case, particles can change, they can collide with each other, they can interact with each other in a lot of different ways, but despite all these internal interactions, the momentum is not going to change when there are no external forces. So let's do an example from the book in which we're looking at, to demonstrate this, in which we're looking at the sticky impact with a simple pendulum. And so here we've got a particle Q, and it's going to collide with particle P. Particle P is starting at rest, and after Q collides with particle P, it's going to stick together, and so then after it sticks, it's going to keep the same velocity with each other, and so we want to find the velocity of this joint particle, PQ, immediately after the collision. So we're going to model this collision from time 1 to time 2, in which it occurs over a very small time period. So to start this out, let's draw a free body diagram of the collision. So we're going to draw a free body diagram in which we have particle Q and we have particle P that are interacting with each other. And so we need to put all the forces on this free body diagram that are occurring on both particles. So on particle Q, we're going to have the mass of Q multiplied times gravity, and this is in the negative EY direction. On particle P, we have the force due to gravity. So it's the mass of P times gravity. It's also in the negative EY direction. Then also recall that particle P is being constrained by the tension in this rod. It's a massless rod, and it's being constrained with a tension that's in at this instant in time, t in the EY direction. In addition to these forces, we have forces that are caused by the interaction between the particles. And so we have a force that's being applied to Q by particle P, and then we also have an equal and opposite force being applied to particle P by Q that we draw in the equal and opposite directions. And so you can see here that we have external forces that are gravity and then the tension in the pendulum itself. And then we have internal forces, which are shown here as Fp, Q and Fq, P. So let's use this information in our equation that we've developed for the change in total linear momentum to solve for the velocity of that combined particle QP, which is what we're looking for. So for this equation, we need to find our total linear momentum at time 2, total linear momentum at time 1, and then the impulse due to the external forces. We've just been looking at these forces, so let's do that part first. So for the impulse due to the external forces, this we know is equal to the integral from time 1 to time 2 of all of our external forces. So we can ignore these internal forces because they cancel out. And for our external forces, we have the tension in the EY direction, and this is minus MQ plus MP G in the EY direction. So it's in the minus EY direction, the force due to gravity on both particles. We're going to take the time derivative of this. Pardon me, not the time derivative, but the integral over time from time 1 to time 2. Alright, so moving on to each of these other sections, we just took care of our external impulse. Now we need to do the linear momentum at time 1 and the linear momentum at time 2. So the linear momentum at time 1, PO as observed in the inertial reference frame at time 1, is going to be equal to MQ multiplied times the velocity of Q with respect to O as observed in the inertial reference frame at time 1 plus MP multiplied times the velocity of P with respect to O as observed in the inertial reference frame at time 1. So we need to find the velocity of Q with respect to O, and so remember Q is traveling and it's going to hit P, which is stationary. So if Q is traveling, we can put some coordinates here. And so an x coordinate and a y coordinate. And so that means that our position vector, r, q with respect to O, is going to be some function x in the ex direction plus y in the ey direction. And then the velocity of q with respect to O, as observed in the inertial reference frame, is simply x dot ex plus y dot ey. And particle P is stationary, so the velocity of P with respect to O, as observed in the inertial reference frame at time 1, is equal to 0. And so our full expression that we plug into our total momentum, change in total momentum equation, is that our total momentum at time 1 is mq x dot ex plus mq y dot ey. Let's solve for our total momentum at time 2. So total momentum, as observed in the inertial reference frame at time 2, is going to be equal to mq, velocity of q, q with respect to O as observed in the inertial reference frame at time 2 plus the mass p multiplied times the velocity of p with respect to O as observed in the inertial reference frame at time 2. And because after it's completed this sticky collision, the velocity, they're stuck together, so the velocity of these two particles are the same. So the velocity of q with respect to O as observed in the inertial reference frame at time 2 is equal to the velocity of p with respect to O as observed in the inertial reference frame at time 2. And so this is going to be equal to x dot of, and let's call this pq in the ex direction, plus y dot of this new particle, pq, in the ey direction. And I just now noticed one thing that I forgot to do up here, and that it's in our velocity of q with respect to O at time 1. This needs to be the x dot q, and this needs to be y dot q. Same way, this needs to be xq, and this needs to be yq on our position vector. So please correct that in your notes. So let's take a look at this expression, and we have x dot pq in the ex direction and y dot pq in the ey direction. Now at time 2, we still have, even though we have a sticky collision, these two guys are stuck together, p hasn't moved. And if p hasn't moved, then it can't have a velocity in the upward direction. This is a stiff rod, it can't move up, it can't move down. And so that means the only velocity that it can have, because it's a simple pendulum, is a velocity in the ex direction. So in this expression here, when these two particles are combined, y dot pq is equal to 0 because that particle together can't move either up or down. And so then we get that our total linear momentum at time 2 is equal to the mass of q plus the mass of p multiplied times x dot pq, and that's only in the ex direction. And so we'll plug all of this into our change in total linear momentum equation. And so when we do this, we get our total linear momentum at time 2, which is mq plus mp multiplied times x dot pq in the ex direction is equal to our total linear momentum at time 1, which is mq x dot in the ex direction plus mq y dot, and this is x dot q and y dot q, did it again, in the ey direction. And then this is going to be plus the integral, so here's our impulse due to external forces, the integral from time 1 to time 2, which is t minus mp plus mq multiplied times g integrated across time, and then this is in the ey direction. And so we have the full expression here, which is in a vector form, and so we have two basis vectors that we're working with in this planar motion, so that means we have two scalar equations. And so if we look in the ex direction, then we get the scalar equation mq plus mp multiplied times x dot pq is equal to mq x dot q. And then in the ey direction, we get a 0 on the left hand side is equal to mq y dot q plus the integral from t1 to t2 across time of t minus mp plus mq multiplied times g dt. So let's take a look at these in a little bit more detail. So in the ex direction, and that was in the horizontal direction, we see that there's no impulse in this equation. Okay, so there's no impulse in the EX direction. And if there's no impulse due to external forces in the EX direction, then that tells us that the total linear momentum was conserved in the EX direction. But because there is an impulse in the EY direction, that means that the total linear momentum was not conserved in that direction. And so hopefully this makes sense, is that we have this particle Q, which impacts P and sticks to it. And when it sticks to it, it loses all velocity that it had in the y dot in the y direction. So any of the y dot momentum it had in the EY direction is absorbed in this direction once it contacts P. However, any of the horizontal velocity or horizontal momentum in the EX direction is now transferred, and then the momentum of the system, we now have two particles moving, and it's going to be at a different velocity, but at that instant in time t2, the momentum is transferred and it's conserved completely in that EX direction. Let's take a closer look at this impulse due to the external forces that we see here. The expression for the impulse itself includes both the tension that's in the cord, or the tension that's in that massless rod, but it also includes an impulse due to gravity, which may seem a little bit strange. And this simply occurs because gravity is a force that's occurring, even though it occurs over a really small time interval. And it occurs over t1 to t2, which has to be small for it to be an impulse. But the momentum itself is taken away from the system, not by the gravity, but it's taken away from the system by the tension that's in the rod. So if we're asked to solve for, or if you're asked to solve for, the impulse within the rod, and so this would be a scalar impulse, this is going to be equal to, as you know, the integral from time 1 to time 2 of the tension dt. And this is equal to negative mq y dot q. And then we're going to add to that the integral of our gravitational force, which is mp plus mq g, so gravitational force, and is the integral evaluated from time 1 to time 2. And so we get from this that the impulse, the scalar impulse, is equal to negative mq y dot q plus mp plus mq g, and then using fundamental theorem of calculus, t2 minus t1. And what this impulse looks like in the rod, or what the force would look like in the rod, we're going to plot tension, and then it's going to be from t1 to t2, is that before the impulse actually occurs, before t1, then the tension in the rod is going to be constant. And it's going to be constantly equal to mp times g. And then, right after the tension, or right after the impulse occurs, it's not going to be constant because it's immediately going to move, but this point is going to be mp plus mg, mq rather, multiplied times g. And so we have an immediate increase to that same level, and then the impulse itself, the remainder of the impulse, is going to look however it looks, and so the area under this part is due to our mq y dot q, and then the area under this part is due to the other part. And that's our mp plus mqg multiplied times t2 minus t1. And so the reason why that this is a positive area right here is actually assuming, I'm drawing it as a positive area because we're assuming that this is a negative y dot, that this is actually coming in at this direction. If this were a positive y dot, then that impulse would go the other direction, and we would see a negative t, or a negative force, within that pendulum rod. So what we've done is we have taken a look at this system in which we have a particle Q that's contacting particle P. They stick together, and then we have a transfer of momentum, a complete conservation of momentum in the EX direction, and then a loss of momentum in the EY direction. And so the initial problem asked us to solve for the velocity right after the impulse occurs, or right after, at time 2, after they stick together. And we only have velocity in the EX direction, and so our velocity is equal to, so this is V PQ with respect to O, as observed in the inertial reference frame, is equal to the mass of Q divided by the mass of Q plus the mass of P, multiplied times x dot Q at time 1. And so we have velocity only in the horizontal direction, so that's in the EX direction. Alright, that does it. I hope you've understood the total linear momentum and can apply that, and I will see you in class.